the most audacious airport construction on the planet.
Kansai Airport Island was the biggest man-made island in the world.
Built at sea to withstand earthquakes and typhoons.
Of course, in Japan, we have many strong earthquakes.
And the pioneering historic innovations.
From an engineering point of view, for that time, it was high advanced technology. It's hard to imagine, I say.
That made the impossible possible. Because of its distinctive landscape, the island nation of Japan has some of the most densely populated areas in the world. With over 127 million inhabitants vying for precious space.
Geography is that Japan is a very heavily populated island. It's double the population of the UK, and although the island is bigger than the UK, 75% of it is mountainous, and about 50% of it is at 45-degree slope, so you can't live on that. So everybody's crammed into the coastal areas and the big cities.
So when it was decided that Japan should attempt to build their first 24-hour airport, it presented its engineers with a unique challenge.
We did not have any space for the airport because almost all the land was very heavily populated. And then there are many residential houses and then the factories.
Their radical solution? To create new land where previously there had been no land at all.
They had no choice. If you wanted the airport to be where people could get to it, it had to be within reach of Osaka. The logical conclusion to that was to go to the difficult place of the Osaka Bay.
They would attempt to create an entire island from scratch, something that had never been done on this scale before.
There was risk, real risk, in trying to build something so big and on such an ambitious scale.
Building in Osaka Bay would mean tackling one of the most hostile environments on Earth, with typhoon winds a regular occurrence.
We have many typhoons coming all region in Japan.
The maximum wind velocity is more than 50 meters per second. Heavy typhoons cause a very big wave, more than the 3 meters.
Earthquakes are a constant risk.
Earthquake is often happen in Japan. Many very strong earthquakes.
And the geological conditions are near impossible.
Perhaps the biggest challenge of all is the weak ground. The ground under the sea at the site that was chosen was so weak that divers would sink into it if they stood on it.
Nevertheless, engineers decided to attempt a feat of impossible engineering and undertake the most ambitious land reclamation project of modern times.
Every project is a challenge, but there is an edge to it when you're stepping out of the known into the unknown.
But building an island at sea was an incredible ambition that would not have been possible without centuries of innovation. Creating usable land from open water has been a challenge throughout history. Prehistoric settlements in Scotland built huts in lochs called crannogs to house large families. Which was fine until the stilts rotted. In Peru, the Uros people of Lake Titicaca built villages on rafts of reeds to prevent attacks by their neighbours, the Incas. But the anchoring system was unreliable. And in the Pacific Ocean, the rulers of the ancient Sodalur dynasty built the offshore islands of Nan Madol from which to rule. But took their secrets of construction to the grave. Thankfully, a more permanent solution to creating new land was on the horizon. To attempt such a daring project, Japanese engineers sought inspiration from a 17th century Dutchman who solved a seemingly impossible land shortage problem of his own. The Netherlands is constantly fighting to keep the North Sea at bay. 1/3 of the land is below sea level, and 65% is vulnerable to flooding. Over the centuries, the country has suffered some catastrophic floods.
We always fight the water because we have to make our land safe. We have to live with the water, but also fight the water.
Today, the Netherlands has the most sophisticated water drainage system in the world. But in the 17th century, dry, usable land was so scarce, the growing population was running out of space to produce food.
They tried to drain these bigger lakes within the sea dike area and the marshlands in North Holland, but a lot of attempts they didn't work. These lakes, they were very deep. It took them several centuries to figure out how to drain them.
But in 1609, engineer Jan Andriaanzoon Leeuwarter came up with an ingenious solution. The son of a miller, Leeuwarter's idea would change the face of the Netherlands forever. Water engineer Nanko Dolman has come to Beemster Polder, where it all began.
What Leeuwarter did here in making this polder dry was a big achievement, and it made him the first hydraulic engineer in the world.
This entire area was once a lake measuring 70 square kilometers and 3 meters deep. Traditionally, windmills were used for water drainage, but they had their limits.
The challenge with windmills like this, they can scoop off 1 meter per windmill.
But as the lake was 3 meters deep, Leeuwarter needed to rethink how the windmills were used. First, he dug a 38-kilometer ring canal around Beemster Lake. He used the excavated soil to create a barrier or dike. He then installed his first windmill, which lifted water from the lake and into the ring canal. What Leeuwarter did next was a stroke of engineering brilliance.
So in the first stage, they could move a scoop only 1 meter of water away. So they would construct and build a second windmill. This windmill would scoop the water, and it will be elevated to the next windmill, and it will be discharging to the ring canal.
The result was a series of windmills placed 1 meter below the previous one. As the water level in the lake dropped out of reach of one windmill, another was installed below. Thus, the water was lifted up in stages until the lake was empty. And the dike protected the new land from further flooding. Leeuwarter used 42 windmills in all. The project took 3 years to complete, and in 1612 the lake was empty and the land ready to cultivate. These reclaimed areas became known as polders.
The Beemster polder was the blueprint of all polders, not only for the Netherlands but also internationally, and it was a real engineering masterpiece.
Leeuwarter had made the impossible possible. Now 50% of the Netherlands is made up of reclaimed land protected by over 12,000 kilometers of dikes and sea defenses. Engineers in Japan needed to take the Dutch principles of reclamation and go one step further. Where engineers in Holland drained lakes to create usable land, Masakai Kitazume and his colleagues would have to build upon land that was underwater and create an island.
So it was a very, very big challenge for us, for the engineers. We construct this island more than 5 kilometers from the coastal area. And also the sea depth was more than 20 meters.
But the biggest challenge was the soft clay ground underneath Osaka Bay. Extending 20 meters below the surface, this weak ground was one of the last places on Earth you would choose to build an island. The clay holds the water like a sponge, And, like a sponge, when you place a heavy object on top, it compresses as the water is forced out, causing the object to sink.
So the best of Japanese technology is required to strengthen that ground below the island, otherwise it would have just vanished.
Engineers knew, left as it was, the island would sink into the waterlogged sea floor. If they could not control how far the island sank, the project would fail. The solution they found was the sand drain.
Main purpose of the sand drain was to speed up the ground settlement.
Sand drains work by providing the water in the ground a shortcut to the surface. Sand is spread across the sea floor. Pipes are driven into it, also filled with sand. The pipes are removed, leaving sand columns behind. The weight of the island will compress the soft clay, squeezing water into and up the columns to escape into the sand layer. This means the island will still sink, but reach its natural depth in a quicker, more controlled way and settle on drier ground. A staggering 1 million 20-metre deep sand drains were installed, the largest operation of its kind in the world. The seabed was ready to take the weight of the biggest man-made island ever built.
The best case scenario was that all would work well and the island would stand, and the worst case scenario was that the whole thing would vanish into the seabed and just keep going.
But engineers had further challenges to face, and they would have to turn to the great innovators of the past.
What we take for granted in our days, that was first time done in this airport.
To produce more impossible engineering. Kansai Airport, Japan, is an engineering wonder of the world, built on its own man-made island in the deep and unpredictable waters of Osaka Bay. Its construction was a seemingly impossible challenge.
We have many technical issues we have to solve to construct this island.
After 2 years tackling nature's most challenging geological conditions, engineers had placed 1 million sand drains into the seabed to help stabilize the ground. But before they could begin the island, they had the daunting task of constructing an 11-kilometer seawall.
The maximum wind speed might be 40 or 50 meters per second, and then the wave height at the typhoon season is more than a couple meters. So the seawall is one of the very important structures for the man-made island.
To begin, divers laid huge foundation stones onto the seabed. Loose rubble was poured on top to build the wall up above the height of the pounding waters of the bay.
If the seawall was damaged, the soil on the island will flow down to the sea.
To stop the rubble wall being eroded by waves and the island washing into Osaka Bay, designers would need to turn to the innovators of the past. In the 1950s, engineering genius Pierre Danel developed a system that would become the world's greatest defense against the pounding sea. At the Laboratoire Dauphinois d'Hydraulique in France, he and his team designed the coastal armor unit known as the tetrapod. At Tokyo's Waseda University, engineer John Batchelor has come to see a demonstration of how the tetrapods work.
There'll be waves at least 3 meters high in a big typhoon, and they pack a lot of punch. So it's very important that the edge of the island is not scoured away by the waves.
The university's wave tank facility can accurately recreate the typhoon conditions that regularly strike Kansai.
2 students down there are putting the model together. They're putting pink pebbles on one side to represent boulders, which would be a very traditional way of protection. And on the other side, they're putting tetrapods like this that link together. It's simulating waves that are about 3 meters high, which is what we'd expect from a big typhoon in the Osaka Bay. So we can see clearly from here that even just with one wave, quite a few of the pink boulders have been washed, some of them right over the island, whereas the tetrapods have all stood firm. And that's because the tetrapods, even though they were lifted by the waves, couldn't be pulled apart because of their shape.
The tetrapod shape also dissipates the force of the waves by allowing water to flow around rather than against it. Since their first installment in 1950, Danel's tetrapods have protected the world's coastlines. At Kansai Airport, tetrapods provided the perfect engineering solution. Nearly 50% of Japan's coastline now relies on tetrapods. The Kansai Airport seawall is one of the largest single applications in the world.
We installed more than 48,000 pieces of the tetrapod. This was a very, very huge number of the tetrapod.
With the seawall complete and protected against the elements, Kansai had a 20-meter deep, 4 by 2.5 kilometer lagoon. Now engineers had the phenomenal task of filling it. In a Herculean operation, 3 mountains were flattened to provide enough rock to fill the hole.
We used more than 180 million cubic meters of the rock on the soil.
80 ships worked for 3 years to ferry the rubble to the site and dump it into the man-made lagoon.
It was a very, very fantastic thing. So many special vessels working there.
In all, the infill was enough to fill 45 football stadiums to the brim. As the surface of the island was leveled off, engineers turned their attention to the terminal building itself. The structure would need to fulfill the requirements of an ultra-modern airport, but also withstand typhoon-strength winds and some of the strongest earthquakes on the planet. Awarded the challenge was architect Renzo Piano, one of those behind the radical Pompidou Center in Paris. And working alongside him was Japanese colleague Noriaki Okabe.
This program asked very big building, 1.7 kilometer building. So we must do something different.
As the island had limited space, there was only room to construct one supersized building which would fit all the functions of a modern airport under one roof. To complete this seemingly impossible challenge, airport designers would draw inspiration from the audacious work of a trailblazing architect of the past. 1930s Berlin was a time of huge change. Germany had grand ambitions, and the city was being overhauled to create a new, modern metropolis. Architect Ernst Sagerbiel was commissioned to replace Berlin's old airport with a new one that would be seen as the gateway to Europe. What Ernst came up with would change the way airports were constructed forever.
Welcome to Tempelhof Airport. We are in the middle of Berlin right now, 2.5 kilometers from the city center.
Tempelhof has been described by architect Norman Foster as the mother of all airports. This 1.2-kilometer building, when constructed, was the longest building in the world. Bernhard Kortz is a German architect who has made a special study of this unique and historic airport.
So this is the main departure lobby, or also arrival hall. Imagine yourself being an air passenger at that time. You're not used to size that big. It was meant to impress all the passengers that would come from Europe, from all over the world. For our times now, it's not that impressive because we know huge skyscrapers, but this building was finished in 1939, so at that time it was highest marvel of engineering in the world.
To create a building this large, Sagerbiel turned to the most cutting-edge techniques of the day.
From an engineering point of view, the whole hall is very interesting because for that time it was high advanced technology.
Sagerbiel used the relatively new system of a steel-reinforced concrete framework, which had incredible load-bearing strength. It was then covered in marble to create a vast, monumental space. But the airport was not only designed to make an impact, but to create a new system.
This building was just looking way forward into the future. This was the first airport that was really designed like an airport as we know it now. All the separation, what we take for granted, that was first time done in this airport.
Tempelhof became the most modern airport in the world. For the first time, there were different areas for passenger arrivals and departures, plus separate gates for each flight, covered by a unique metal canopy.
This is where your plane would wait for you. This incredible space is also an engineering masterpiece.
The canopy runs along the side of the building for 400 meters. Ingeniously, the weight of the canopy is counterbalanced by a steel wire hidden in the fabric of the building.
By using that construction, they could achieve a very thin and light structure. You have a huge spanning roof where you can actually enter with the whole plane. So even when it's raining or snowing or stormy, you can enter on dry foot. And additional, your luggage you don't have to carry yourself. So the whole situation was just totally, completely different from any other airport at that time. It's hard to imagine, I say.
Tempelhof achieved what no airport had done before. It pushed engineering to its limits with its daring design and created a concept that would become the blueprint of all modern airports. "6,000 miles away at Kansai Airport, architects and engineers have taken this concept of airport design to a whole new level. Just like Tempelhof, when built, Kansai was the longest building in the world. Architects designed a sleek glider-shaped terminal, its main atrium a soaring 30 meters high, connecting to a uniquely curved wing-shaped departure concourse that measures a staggering 1.7 kilometers.
I think Kansai International Airport, this shape and space is unique. Kansai is huge, but you feel very human scales.
But the real design challenge was how to create a building that would not fail when attacked by the forces of nature.
We must be very, very careful this natural strong force.
Kansai Airport in Osaka Bay, a hub of futuristic design. This wing-shaped terminal, when built, was the longest building in the world. It has 41 gates, handles millions of passengers a year, and is Japan's first 24-hour airport. But building an airport terminal in an area prone to violent earthquakes presented architects with some near impossible design challenges.
Of course, in Japan, we have many strong earthquakes. Engineering point of view, architecture point of view, we must be very, very careful. This natural strong force, we must consider all of them. That is very, very important challenge.
To prevent the building suffering from a catastrophic failure, engineers had to design a system that would withstand huge force.
Building design is that we have many mechanical systems for the joint absorbing earthquakes.
The key solution was to make sure that every part of the building could move independently.
This bridge must be flexible. So when earthquake attack, this handrail is moving like that, absorbs the movement. This wall is moving like that, absorbs the movement. Floor is moving like that, absorbs the movement.
As well as movement-absorbing joints, engineers needed an additional system to construct the 4,000 square metre glass walls.
This is window, huge windows. It takes some movement of the earthquakes. We use for the gasket system. If the movement coming, it's absorbed with rubbers, better than another system.
Glass cannot dissipate energy as it's too brittle. The rubber gasket around each pane absorbs any seismic energy and allows each one to move individually. In all, 5,000 glass panels were installed. The terminal was constructed over a period of 3 years by over 10,000 designers, engineers and workers from across the globe. But soon after completion, the airport design faced the ultimate challenge.
1 month after the opening, a typhoon attacked this Kansai International Airport. And 4 months later, we had Kobe earthquakes. So we were tested.
In January 1995, Kobe earthquake struck the Osaka Bay region, killing more than 6,500 people and damaging over 150,000 buildings. But Kansai Airport passed the test, and not so much as a single pane of glass was broken. Since then, Kansai International has seen nearly 2.5 million flights, carrying 300 million passengers. But a century earlier, this incredible 24-hour stream of incoming and outgoing aircraft would have been totally impossible. The roots of civil aviation began after the First World War. Passenger planes were for the daring few, often converted bombers, flown by ex-military pilots. Scientist Andrew Steele is getting a taste of flying from the days when rules were few and only the brave took to the air.
Would you go for a gentle loop-the-loop?
Yeah.
Pop the nose down, increase the speed to 100 knots. Now look up. That's it. All the way up. All the way up. All the way over.
Oh, and the whole planet is upside down. That was amazing.
And back to
Wow.
Woohoo! And back to
It's unthinkable today, but in the days before air traffic control, flying was largely unregulated. Pilots had to rely solely on what they could see to avoid mid-air collisions.
There's another aeroplane. So we just had a Cessna fly past our right wing, and the only way that I know that is because the pilot was kind enough to point it out for me. There's no radar or other instruments in the plane that allow us to know where other planes are in the sky.
Pilots also relied on the most basic of navigation.
For me, the only way that I can tell where I am is by looking at the ground underneath me and comparing that to a map.
After the First World War, landing strips used by fighter planes became designated flying sites, or airports. And by the early 1920s, Croydon Airport near London was the busiest in the world. But as traffic intensified, it was clear that if chaos in the skies was to be averted, a new solution would be needed. It was Croydon's chief radio operator, Jimmy Jeffs, who, using the plane's ability to transmit a simple signal, invented a system that we now recognise as the first air traffic control.
The system they came up with was called triangulation, and it works like this. Imagine there's a plane over there, and I want to know exactly where it is. Now, I can get that plane to start broadcasting a radio signal. I can then look around and find out the direction in which that signal is strongest. And then I know that the plane is somewhere along that line. In order to work out exactly where it is, though, I'm going to need to go upstairs.
The radio operators tracked the plane's signals from a tower, which gave them a bird's eye view of the airfield.
So this is where the radio operator would have sat, wearing some headphones like this, and he'd have listened out for the bearing the plane was coming in on, the strongest direction of that radio signal. So if you listen carefully, there we go. I think the bearing is about 185 degrees. So it's time to move over to the triangulation chart. We're here in Croydon, and the bearing that I got was 185 degrees. And now we know the plane is somewhere along that line, but we don't know where. The great innovation from here in Croydon was to realise that we could ask another radio receiving station that also had a directional aerial. So we might try this one in Lymm. And these guys reported a bearing of 254 degrees. So let me just, there we go, line that up. Now, using these two bearings, you can see where they cross, X marks the spot, that's where the plane is. And if we want to be doubly sure, we could ask a third radio receiving station. So these guys up here in Fulham, they report a bearing of 206 degrees. So that third bearing from Fulham confirms what we thought. The plane is definitely over Brighton. So we can move over to the plotting chart, grab a pin, and there we go, position that incoming aircraft. And now not only do we know where that aircraft is, but we've got the positions of all the other aircraft too, so we can make sure they're not going to crash into each other.
Thanks to this innovation, pilots knew where they were and could find destinations, making scheduled flights a reality. In 1922, Jeffs was issued with Air Traffic Control Licence number 1 and became the world's first air traffic controller. Controllers at Kansai still rely on the same basic principles to keep track of planes in its airspace. Today, the system also displays aircraft identification numbers and records of speed and altitude. As well as ground-based receivers for triangulation, the signals are now detected by a network of satellites called a global positioning system. This cutting-edge technology allows planes to take off and land every 4 minutes, 24 hours a day. But to keep the airport running and catastrophe at bay, Kansai would need to employ one more piece of impossible engineering.
This place is a sort of hidden place. Only the few people know this system.
Kansai Airport in Osaka Bay, Japan. The first airport built on its own specially created island. This unique single structure, welcoming millions of passengers each year, connecting to 25 countries, is one of Japan's leading air terminals. Engineers overcame extraordinary challenges to create a cutting-edge building capable of withstanding powerful seismic forces.
We had a very good team, both engineer team. I think Kansai is one of the unique buildings still.
But Kansai would need to produce more impossible engineering. After stabilizing the seabed, the island was predicted to sink by up to 6 meters. But after 3 years, it had already sunk by over 8 meters and was still going down. And it soon became clear parts of the island were settling at different rates, putting unequal stress on the terminal structure.
Such an uneven settlement may cause some cracks of the buildings or some disconnections of the cables or the pipe or like that.
If too much strain was placed on one section of the building, it could subside. To hold the terminal's enormous weight and save it from collapse, engineers would need to turn to a groundbreaking innovation from the past. Humans have always had great ambition to build big. But to lift huge weight, muscle power was not enough. The ancient Greeks built the first crane using a simple pulley. Lots of power generated by just a few men. But it was hard to control. Leonardo da Vinci invented the screw jack that could lift weight from below, transferring rotary motion to linear. But this still relied on human strength. Finally, in the 19th century, tired New York mechanic Richard Dudgeon had an idea. He boosted human power with hydraulic power. His new jack compressed oil from a narrow cylinder into a wider one. The pressure in the second cylinder was equal to the first multiplied by its size, therefore lifting more weight. Engineers at Kansai have taken this innovation and used it in a remarkable way.
This place is a sort of hidden place. Only the few people know this system.
A system that thousands of daily passengers above are completely unaware of.
This is a jack-up system, and then this is the hydraulic jack.
In the basement of the terminal building, 900 fully automated individual hydraulic jacks have been installed to counteract any uneven settlement. Sensors in a control room detect when one part of the building is out of kilter with the rest. Each jack, capable of lifting 300 tons, can be activated individually. Steel wedges are used to support the building at the new height.
You can see many steel plates. The thickness is about 10 or 15 centimeters.
The technique is repeated until the terminal is level. Without this innovation, the whole building would have failed.
If this system is not here, then the ground settlement may cause very severe damage to the building itself.
Engineers at Kansai have employed many unique systems of engineering to adapt to the island's environment. The single terminal building is a design masterpiece. But there is one system, the stacking of departures directly above the arrival floor, which is key to the building's success.
I think if you imagine for the domestic international separately, we need more space in the surface. This sandwich system, this is the first time in the international airport system in the world.
But with hundreds of flights a day, carrying up to 50,000 passengers with thousands of items of luggage, the challenge of moving bags between floors, security checking and delivering them to the right place on time, in a building nearly 2 kilometers long, posed a very specific conundrum.
I think baggage handling is so important in the airport terminal building and not easy.
The solution owes an enormous debt to the key innovators of the world's industrial past. The Industrial Revolution was a pivotal moment in history. It marked the transition from manpower to machine power. Whilst it was the steam engine that provided that crucial power, key to driving the revolution forward was the conveyor belt. Professor Andrew Steele is finding out why.
The basic principle behind a conveyor belt is actually very simple. What you need is a series of rollers and then stretch a belt around those rollers. By turning the roller, the material then moves. For example, if I place an object on this end of the conveyor belt and then provide power to the drive pulley, use this rotational power that I might get out of a steam engine, for example, to move the object linearly along the belt.
Conveyors were initially flat, made of wooden rollers and belts of cloth, which restricted durability and capacity. However, in 1891, American industrialist Thomas Robbins realized their potential. His contribution was to supercharge the industrial world.
Firstly, he took the flimsy material of the belt and coated it in rubber, which made the belt itself a lot tougher. And secondly, he developed this 3-point roller system, which curves the belt into a U-shape and stops the rocks from falling off.
Robbins' robust conveyors could now carry hard, heavy substances, and when applied below ground, transformed the coal mining industry, fueling manufacturing around the world. Robbins' development of the conveyor belt paved the way for its adaptation across the industrial spectrum. Modern manufacturing now uses a variety of fully automated conveyor assembly lines with innovative features of their own.
One of the key differences between these modern conveyor belts and the more simple original versions is that these can go round corners. And the way that works is that rather than being a belt of material, they're actually made up of a series of interlinked bits of metal, which allows it to articulate in different directions.
Thanks to the innovators of the past, advanced conveyor belt systems are now integral to our everyday life, from manufacturing to mining and even restaurants. At Kansai Airport, designers have incorporated many cutting-edge innovations into their luggage conveyor belt system and created something special. The unique challenge within the compact terminal was to get baggage from international check-in on the top floor to the aircraft 14 meters below.
We can't make this sort of a system because we have no space to do that.
What the designers came up with was the tallest spiral baggage conveyor system in the world, measuring 700 meters in total, that transports over 10,000 items of luggage each day.
I think the spiral system is a very good choice.
But crucial to efficiency is the tracking system. Each bag is barcoded and special sensors track its progress along the conveyor. When it reaches the correct floor, a 3D tilt tray is activated, releasing the bag, so that 3.5 million items reach their correct destination each year.
This airport works well, and I think I'm very proud of that.
It took 20 years from conception through construction to raise an entire island from the depths of Osaka Bay and create a leading international airport capable of withstanding nature's most violent attacks. But by drawing on the innovations of the past, adapting, improving them, and making groundbreaking innovations of their own, the engineers, designers, and workers on the Kansai Airport overcame extraordinary obstacles and succeeded in making the impossible possible.
Kansai Airport Island was the biggest man-made island in the world. Every engineers and every people involved in this project believes that we achieved the impossible.